Okay, welcome everybody to our lecture on algorithmic meta theorems. Today we're going to continue our proof on Courcelle theorem and finish the chapter on Courcelle theorem and start already looking at what comes next. But before we go there, let's maybe start with a quick recap of what we did before. So we introduced Courcelle theorem and all the different variants of it, MSO1, MSO2, counting MSO, where it had its parity constraints, and we considered optimization variant as well. And we started proving the simple MSO1 base variant. And the statement was the following: we're given an MSO1 formula phi in the graph, and we should decide whether the formula holds on the graph or not. In the running time, that is some function of the tree width and the formula times a linear factor in n. And we were about to do this using Courcelle's theorem. Using the Fifferman-Watt theorem. And the way we proceeded was as follows. We were assuming that we had a nice tree decomposition given with this join and introduce and forget nodes. And we're mostly focusing on the join operation because we'll see that this one's like the most complicated one and the other ones will follow nicely once we have the machinery for the join operation. And for the join operation, we had this bag with vertices v1 to vk, and the two children bag contained the same vertices v1 to vk. So the picture was kind of like this. If f are the vertices in the left subtree and h are the vertices in the right subtree, then they induce two subgraphs where the intersection or the boundary between the two graphs is exactly the vertices v1 to vk that are in the bag that we're currently considering. And so we defined the notion of Q-type. So the Q-type, it depended on some graph H and some vertices v1 to vk, which are the vertices inside the boundary. And we then said that the Q-type of H on these boundary vertices is simply the set of MSO1 formulas with k free variables. So for every vertex in the boundary, we have one free variable, and they should have quantifier rank at both Q, and we put them then into the type if and only if the formula holds after plugging in the free the variables of the boundary v1 to vk. And these Q types, they can be composed nicely, and that's what the Fifferman-Watt theorem says. It says if we know the Q type of f on the boundary and the Q type of h on the boundary, then from this we can deduce the Q type on the union of the two graphs. So far, so good. We wanted to do dynamic programming now, and in order to do that, we need to fix our Q. So if in the end we want to evaluate the formula phi of quantifier rank Q, then this is the Q for which we're going to compute our Q types. And the way we define our records was like this. We have a table for the bag I, we have table mi, and then we've put the formula xi into the table with the number 1 if xi holds on the vertices below the current bag and 0 otherwise. And this way we store the truth value of all formulas of quantifier rank Q whose variables correspond to the vertices of the bag. So in a sense, we store everything that MSO1 can say about the graph below the current bag specifically, and also about the vertices in the bag. And what we're not quite finished, what we didn't quite finish last time was proving that the Q types are in fact small. So we need to, of course, show that the information that we're storing in the tables has only some size that depends on the tree width and the length of the formula. And we're about to do just that. So the exact statement that we need is we have to show that the number of formulas psi of quantifier rank at most q with at most tree width plus 1 free variables is bounded by some function of the tree width and of the length of the formula. And if we have that, then this bounds our record sizes. And we did some simple pre-processing things. The first thing we did, we assumed that the number of colors in the graph can be bounded by the length of phi. So if, for example, there's red vertices in the graph, but the formula phi that we evaluate in the end, it doesn't mention any red vertices, then we can just remove the color red from the graph and we don't have to talk about it anymore. So this way we can assume that the number of colors is bound by the length of the formula. And next we can reduce some redundant literals in the formula. We will see soon how that works, but the general principle is if something occurs more often than it needs to, like here x is equal to x and x is equal to x, then it's kind of redundant and we can remove the duplicates, and this way our formulas will become short. So we'll prove this by induction with the base claim being q equal to 0. So we have quantifier-free formulas. And I want to argue that the number of quantifier-free formulas with at most k variables will be 2 to the 2 to the O of k squared phi. So it's double exponential, but it depends only on the number of. Oh, it's not very visible. Oh, what's strange here? Somehow it's not synchronizing the slate. But here's the statement. Okay, so the number of variables, the number of different formulas quantifier-free should be 2 to the O of k squared length of phi. And how do we prove that? So at first, let's talk about all the different literals that there can be. So we can interpret our formula as formulas in CNF form. So we can rearrange them always such that they're a conjunction of disjunctive clauses. So something like A or B, that's one clause, and C or D, where A, B, C, D are literals. And first, let's bound the number of literals in such CNF formula. So we can talk about the colors of the vertices. So for the ith variable, we can say that it has color J, or differently for the j's variable, we can say that it is color I. And we have phi different colors, and we have k different variables. So in total, that would be k times phi different literals of this type. Similarly, we can say that some variables are equal. So there's now k times k different literals like this. Or we can say that they're adjacent, another k times k literals. And we can, of course, have their negations. So in total, this means that the number of literals that we have would be k squared times phi. That's an upper bound on it. And next, if we consider clauses, a clause, you can see it as a subset of the literals. So we will, if we don't allow duplicate literals, because if a literal occurs twice, we can always remove it and the formula stays the same. So we can assume that every literal occurs either 0 times or 1 time. So for every literal, we have 2 options. So the number of different clauses is then simply 2 to the number of different literals. So after removing duplicates, the number of possible clauses is 2 to the number of literals. And we can do the same thing with the number of different formulas, because every formula can be again seen as a set of clauses. So every clause is either there or not there, and we can remove duplicate clauses. So this way we get another exponential factor. In total, this is where the double exponential comes from. And this is our base case of the induction, which has proved that there's only relatively few different quantifier-free formulas with a bounded number of variables. And next, we want to make the induction step. So now Q is no longer 0, but it's any number. And we want to show that there's only a limited number of formulas with quantifier rank at most q and at most k free variables. And what we assume is that we have a bound on the number of formulas with quantifier rank at most q minus 1, but one more free variable. So this one free variable that there will be more, this is the variable that we will quantify over to increase the quantifier rank. And the number of these formulas, let's assume that they're xi1 to xi(l). So we have L of these formulas, and we said that we can write our formulas as C and F formula. So then our formulas of quantifier rank at most q, they look something like this. So we can have Boolean combinations, or a Boolean combination of different formulas that have quantifier rank 1 less. No, not quite. So anyways, our formulas look like this. Here it can be like this. The variable can be existentially quantified, or another universally quantified, existentially quantified. And after such a quantifier comes a formula which has one quantifier rank less, but it has one more free variable. So this variable x, that is now a free variable. And this is exactly the kind of formulas that we assume we have a bound on. So in general, we can assume that our formulas are conjunctions, how did I write it here? I wrote it as disjunctions of conjunctive clauses, but it doesn't matter which way you see it. And here it can be like 2 to the L different clauses, because we can have or actually 2 to the 2L, I think. Because there's L different xi's, and each xi can occur either with a universal or with an existential quantifier. So we get something like 2 to the 2L. And then this is the number of different clauses, and then the number of different formulas is 2 to the number of different clauses. So that's 2 to the 2L. And this should be then an upper bound on the number of formulas with quantifier rank at most q and at most k free variables. And so we notice that with if we increase q, we always get the tower increases by 2 steps. So in total, the number of formulas of this kind are 2 to the 2 to the 2, and then we have this base term, tree width squared times phi, and the height of this tower is 2q, 2 steps for every quantifier, for the quantifier depth, each step. But yeah, this is a function of the tree width and the formula. So this is the thing that we wanted to show. And so our records are relatively small, even though this is, of course, a very huge function. And unfortunately, this bounded kind of, yeah, a question?
Yeah, I think I missed something. Where is it now? Tree width? Where's the tree width coming from in this bound?
Yeah, the tree width is coming from the number of free variables. So on the base case, we assumed we had k free variables. And so, but now for every quantifier rank step, we add another +1 to the number of free variables. But if our formula with quantifier rank q has at most tree width many free variables, then in the base case, the step 1 has tree width plus q free variables. And some stuff is swallowed in the O notation, I guess, hopefully.
Okay.
Maybe there's another, maybe the exponents are not quite right. But I think this is roughly exact. Okay. So I think after we've bounded the size of our tables, it's now time to actually compute these tables. So just as a reminder, we have this tables MI. For a bag I, we have a table MI, which contains those formulas that are evaluated on the vertices below the bag. And of course, we want to compute these values the way we usually do in a bottom-up fashion, starting with the leaves. And for the leaves, this is actually pretty empty, pretty easy because the leaves are empty and we have no free variables. So the graph that we evaluated on is simply the empty graph. And then our records mi for leaf I would be simply all sentences with quantifier record was q that hold on the empty graph. So usually we would have formulas psi x1 to xk, but now with no variables, so it's simply psi without any free variables. So it's sentences, and of course we can evaluate sentences on the empty graph. This is pretty cheap, and so this way we can fill up our record tables for the leaves by simply evaluating them. Gets more interesting now with the join operation. So for the join operation, looks like this. We have our bag I, and since it's a nice decomposition, we have bags J and bags L below that contain the same variables and that contain the same vertices inside the bag. And now let's translate our notion for our record tables to the notion that we used for Pfefferman-Watt. So let's say F is the graph that contains the vertices below bag J, and similarly H is the graph that contains the vertices below bag L. Then our records for bag J does exactly the Q type of F on the vertices inside the bag. So there's a one-to-one correspondence between the Q type and our record for a bag J. And of course, the Q type is computed on the vertices V1 to Vk. And similarly, ML is the Q type of H on our boundary vertices. And what we want to then compute is our records on the graph G of the V1. So the graph induced on the vertices below bag I, but this is simply the union of F and H. So the picture looks like this. We have F and we have H, and the vertices in the intersection of F and H are exactly the vertices that are in the boundary or in the bag. And our records for I are equivalent to the Q type of union F and H on our boundary vertices. And this is something we've talked about for quite some time now. This is exactly what Pfefferman-Watt gives us. So we can compute the Q types from the Q types of F and H. And this gives us then our records Mi psi. Other questions about this so far?
Behind these new record is something that everything that we get by treating Pfefferman-Watt as a black box. Right? You don't exactly know the mechanism, so how one can combine records from F and H to obtain.
Yeah, we don't know exactly how Pfefferman-Watt does it, but it says is that there is some computational procedure that if you plug in the type here and the type there, then you get the output, the new type. And this is a function that we can just call and use the output of. So the first exercise of the current sheet, it gives a bit more insight on how these functions are computed, but not so much more. Any other questions? Then let's go to the introduce case. So we will cheat a little bit and interpret our introduce operation as a mini join operation to also use Pfefferman-Watt. And the way we can do it is as follows. So now we have a bag I that introduces a vertex vk plus 1. So this vk plus 1 is not yet present in the back below, but now it's suddenly present. And here, let's first interpret what is in the back below. Let's say f is the graph that contains all the vertices below back j. And then our records mj contain the q-type of f on v1 to vk. So far, so standard. But now we want to introduce this next vertex vk plus 1. And our graph h that we will use for Pfeffmann-Ward, it will be a rather small graph. It will be just the graph g induced on v1 to vk plus 1. So it contains exactly the vertices that are in the back of I. And what we want to compute then are, or what we can now compute using brute force, is the q-type of h on v1 to vk plus 1. So the size of h is bounded. Its size simply k plus 1. So it's rather small, and we can evaluate all formulas of quantifier rank at most q on this small graph. And this way we get the q-type on h. And now we have two graphs, f and h, and the q-types of them. And the thing that we want to compute, it can be seen as a q-type on f union h. So we want to compute the truth values of formulas in the graph g vi, and vi, it contains all the vertices that are below this back, so this part of the graph. And this is simply f union vk plus 1. So we need to add a single vertex to f, and our graph h does exactly that. It adds a single vertex only to our graph. And the new thing is that we now need to compute the q-type on the larger boundary, on v1 to vk plus 1. So this is a little bit different. Now the boundary changed. So we have stored the q-type on v1 to vk, but we need the q-type on v1 to k plus 1, vk plus 1. The usual version of Pfeffmann-Ward doesn't quite give it to us. So here the boundary is 3 times the same thing. But luckily, there's a more advanced version, or phrased differently, the version that I presented you so far is a bit reduced. You can buff it up a bit and formulate the Pfeffmann-Ward theorem also like this. So this is another way to phrase it. In fact, if you have a boundary here and you have another boundary here, then you can even get the union of the two sets here. So in particular, we know the q-type on v1 to vk and the q-type on v1 to vk plus 1. Then Pfeffmann-Ward even gives us the q-type of the union on v1 to vk plus 1. And this is exactly the thing that we need for our records here. And this is how the introduce operation works. Other questions on this?
So this graph H is just the boundary vertices and doesn't involve the remaining vertices from back J.
Yeah, H contains only the back I. So the intersection of H and F is exactly here in this back. At last, there's the forget operation. The forget operation will sound a bit strange, but because it kind of sounds too simple to be true, but it actually is. It works like this. So for the forget operation, we notice that the vertices below the back actually stay exactly the same. So the vertices below back I and back J, they induce the same graph. And then What we have already is the record on J, which are formulas with the three variables x1 to xk that are evaluated on v1 to vk. And what we want is we want to forget the vertex vk. So we want formulas over x1 to xk minus 1 that are evaluated on v1 to vk minus 1. But what we want is a subset of what we have. So if we know the formulas on x1 to xk, then in particular, we also know the truth values of the formulas on one variable less. Because it could be like the formulas, they don't have to use the variables. So the variables can be officially part of the input, but it doesn't need to be used. So we also have the truth values on these formulas where the variable is not used. So this gives us the records for the bag that is one smaller. And the questions about this operation?
But these are not completely the same. These are just the formulas that would take xk as an input and wouldn't use it in the formula, and therefore we can consider them as formulas that take one less variable as an input.
Yeah, so this is now a bit of a syntactical difference. Like on the one hand, we have formulas that take it as an input but don't use it. These formulas we have. But what we want is formulas that don't take it as an input and don't even use it.
Okay. But it does definitely reduce the amount of formulas that we say.
Yes.
Okay.
So the formulas that use xk, we throw them away, and we only keep those formulas that don't use xk and interpret them as formulas that don't even have xk as an input. And now we covered all the operations of the dynamic programming. And in summary, what we get, we find out that we can evaluate formulas phi on the graph G, and the running time is this horrible function. It is a tower function. The height depends on the length phi, and in the top, there's the tree width and the length of phi again. And where does this running time come from? Because all these operations that we did, they are like a single step is kind of linear in the size of each record. And each record has exactly this size. And for the dynamic programming, there's usually roughly n steps that we need to do to traverse of the tree, because the tree has roughly n bags. So this is the running time that we get. This function for every single operation, and we need to do n steps in the decomposition.
The training channel that we saw before is specified the height of the tower as 2q over 2π.
Yes, so before we wrote here 2q, but this is upper bounded by 2 phi. Like I didn't want to express the running time as a function of q. I wanted to simplify it a bit. But you're right in the sense that evaluating formulas of low quantifier depth, but that are very large, is comparatively cheaper because the height of the tower grows smaller. And now you may be wondering whether this horrible tower can be improved. And there's a negative result by Frick and Courcelle, which states basically that you cannot get rid of this tower function if you want to solve MSO on tree width, or even if you want to solve it on trees, then you always need the height of such a tower. I don't know what the optimal height is, but the height somehow depends on the length of the formula or the quantifier depth. And this is why usually you would consider Courcelle theorem as some kind of theoretical classification tool. So it gives you a very quick idea on whether a problem can be solved on tree width or cannot be solved on tree width, because you only have to write down an equivalent formula. But usually, if you want to actually implement the problem, you wouldn't use Courcelle theorem. You would like tailor a dynamic program specifically to the problem at hand using some heuristics, maybe, I don't know. But actually, Courcelle theorem has been implemented. So if you do it the way we just described it, then of course the running time is very horrible if you want to keep track of all the Q types because they're just so big. But the way they implemented it, they used some kind of implicit representation of the Q type. So they stored some kind of game trees. So the evaluation of MSO formulas, you can see it as a game between the existential player and the universal player. And then you can store for like all the different moves that a player can make. Either it picks a vertex from the boundary, or it picks a vertex that has been forgotten already, or it will pick a vertex that lies in the future somewhere and will be revealed only later on. So you can store these kind of trees, and they tend to be a much nicer compression and much smaller than storing the Q type the way we just did it. So yeah, this has been implemented and it's on GitHub, and you can check it out if you like. And the way you would program it is like this. So you can give it an MSO formula as an input. So this is a formula that would express 3 coloring. So you have all this MSO logic. You can write that a vertex is in a set and that they're adjacent or not adjacent. And yeah, and then you can evaluate it. And I'm not quite sure up to which tree width it works, but if the tree width is low enough, then you get an output in reasonable time. And on some inputs, I've heard that it can even beat like the standard CPLAX tools and stuff like that. Okay, to wrap it up, this proof, I wanted to mention briefly that what we just did, it works for the base variant, deciding whether the formula of MSO1 is true. We saw already how to lift it to MSO2, but you can also, there's a Pfefferman-Watt theorem also for CMSO, this logic with the parity operations. So if you plug in the different Pfefferman-Watt theorem, then the proof goes through exactly like that, and you get the Pfefferman-Watt theorem for the richer logic. And if you're interested in the optimization variant, then you store not only whether a formula is true, but you also store the largest set that makes the formula true, or the smallest set if you're trying to minimize something. And so in a similar fashion, by blowing up the records a little bit, you can also do the optimization variant of Courcelle theorem. Yeah.
You know, that's also part of the implementation, I think.
Oh yeah, they also, their implementation also works for optimization problems. Their implementation even works for counting the number of assignments. So something like counting the number of independent sets of size 50 or stuff like that, I think. Okay, are there any questions first about like wrapping this up on tree width? If not, then I briefly wanted to mention dense graphs as well. So if a graph contains a clique of size k, then the tree width is at least k+1. So if you have a graph with very large cliques, then naturally the tree width is very large, and Courcelle theorem doesn't give you anything because the runtime is too bad. But there is a width measure that also works for such dense graphs. So the notion of clique width is very similar to tree width in the sense that it's more general than tree width. And for this width measure, cliques have a width of 1. And the MSO1 model checking still works on graph of bounded clique width, but MSO2 breaks down. With last lecture, we saw that dense graphs tend to be quite complicated from the perspective of MSO2. But let's talk a bit about what this mysterious clique width is. So a clique width it for ClickWidth describes graphs using a sequence of compositions. So here you see the final output of the click decomposition here. This is the graph that we're interested in. And then you see some kind of tree that builds this output graph using our simple operations. We'll soon talk about what kind of operations you can use to build the graph of bounded ClickWidth. But you start with very simple graphs, like single vertices, like here. These are the leaves of your decomposition tree. And then you can, for example, here, you build the union of two leaves. So here you have, what is it? Green and a blue leaf, and you just build the disjoint union of these two vertices. And so, and you notice that the vertices have colors, and the decomposition rules, they will be able to make use of the colors. So the more colors you have, the more complicated graphs you can build, and ClickWidth will be the minimum colors that are needed to construct graphs using the following 4 operations. So let's talk about what kind of operations you can use. So what you can do first is you can create a new vertex of a color I. So this is what is done to create the leaves of the graph. Here you create a green graph, you create a blue graph. And so this way you can create single vertices. And the next operation you can do is you can create the disjoint union of two graphs. So this is what happened here. You just build the union of the green and the blue vertex, and you get a new graph. The third operation you're allowed to do is you can say connect every vertex that is green to every vertex that is blue. So for every color I and color J, you can connect all vertices of color I with all vertices of color J. And this is what happens here. In the step between these two things, you said connect everything that is green to everything that is blue, and you get a new graph. And so with these 3 operations, we can get already quite far. Here, if we start here, we create 2 vertices, make the disjoint union, color the connection between blue and green. Here we also create 4 single vertices. And then this graph here is simply obtained by creating the union of these 2 graphs. Next, we create all the edges between the red and the blue vertices. And the last rule says that we're allowed to change the color between of a vertex. So here, to go to the next graph, we say color every green vertex blue. And so this way we get the next graph. On the right side, we can do similar kinds of operations. And in the end, we get our output graph. And since we only used how many colors? I think 3. We would say that the ClickWidth of this graph is 3. And why is ClickWidth nice? So the first nice thing about it is that graphs of bounded tree width also have bounded ClickWidth. So if the ClickWidth is W, then the tree width is W, then the ClickWidth is at most some exponential function of W. And so I already mentioned Courcelle theorem, and it's for graphs of bounded ClickWidth, get the following result. If you have an MSO sentence phi and the graph G, then you can decide whether the formula is true on the graph or not in some function of the ClickWidth and the formula length, and now a cubic factor in n. And so this is now new that the runtime is only cubic in n and no longer linear. But it's also necessary that it's no longer linear because the graph can have quadratic number of edges, so it needs to be at least quadratic in n. And this cubic factor, you get it for computing such a decomposition tree. And so the first thing you would need to do if you want to do this model checking without the ClickWidth is you compute this decomposition tree in cubic time, and then you can use again Pfefferman-Ward. So you want to basically compute the Q type of every vertex in this decomposition tree. And if you have the Q type for the root, then you can check whether the formula is true or not that you're interested in. And the computation works again using Pfefferman-Ward. So for single vertices, you can compute the Q-type using brute force. And then if you create the disjoint union between two vertices, two graphs, you can post them using Pfefferman-Watt. And the new thing is now these, if you want to add edges between two colors, then you do a simple replacement of the formula. So let's say you want to know for this graph, you have a formula that states are there two vertices that are adjacent, but you cannot evaluate them on this graph yet. But you have the predecessor in the decomposition where an edge has not been inserted yet. So then you would ask, in this graph, you ask instead, are two vertices adjacent, or is one vertex green and the other vertex blue? So this formula is true in the graph above if the unmodified formula is true in the graph below. And so this formula that modified a little bit, it is also bounded quantified depth, and you can check the Q-type whether the modified formula is true on the predecessor in the decomposition. So using simple formula rewritement, you can also keep track of these edge additions and vertex recolorings. And the main complexity actually is again captured by the Pfefferman-Watt theorem. And yeah, that's all I wanted to say about click width. Other questions about it? If not, then I would like to completely change the topic. We would go back to the first lecture again and maybe recap a little bit of what we did already and then take an outlook of what we want to do next. So in the first lecture, we were considering the independent set problem, and we noticed that using dynamic programming, you can solve it actually on trees. And we've kind of pushed this dynamic programming to the limit using Courcelle theorem. We introduced tree width, and the same principle of dynamic programming also holds in graphs of bounded tree width. And it holds not only for independent set, but for much more complicated formulas. Everything that can be expressible in MSO2 can be solved in graphs of bounded tree width. And after considering independent sets and trees, in the first lecture, we asked next, what can we do about planar graphs, for example? And there we had first some bad news that independent set is NP complete on planar graphs. So we cannot get the same kind of independent set algorithm. And in particular, we cannot do MSO model checking into planar graphs, because then we would in particular solve independent set in polynomial time. But what we did discover, if we have a graph, if we have a planar graph, then we can find small independent sets. So if we're interested in an independent set of size k, then we can find it in a planar graph in time 6 to the k times n. So the running time will be linear in the size of the graph, but we have this additional factor that is some exponential function in the size of the independent set that we're looking for. So if we're looking for a small independent set, then 6 to the k would still be small, and we would consider this algorithm rather efficient. But as soon as the independent set that we're looking for is rather large, then we can't do much anymore. And the way we discovered this algorithm was a simple branching algorithm. In a planar graph, there's always a vertex of degree at most 5. And then for an independent set, if we're looking for an optimal solution, then either the vertex itself or one of its 5 neighbors needs to be in the solution. And this is something we can branch over and reduce our k this way. So picture that we drew in the first lecture was like this. So on trees, we could solve independent set in linear time. And then on the more general class of planar graphs, it would still be fixed parameter tractable. So we could solve it in a running time that is exponential in the solution size, but linear in the size of the graph. And I promised you that we would generalize this result. So we would introduce the notion of tree width and notion of nowhere dense graph classes. And the picture would look like this, where before, here for trees, we had polynomial time. For planar graphs, we had FPT time. And for here, we had hardness. The picture looks like this. For tree width, we have polynomial time. For lower dense graph classes, we will have FPT time. And in general, we would have hardness on general graphs. So in the following lectures, I will introduce this notion of lower denseness at some point. And in general, we will talk about certain classes that generalize planar graphs and bounded tree width graphs and many other sparse graph classes. But in order to do that, we first need to augment our notation, our way of talking about graphs and graph classes. So far we considered width measures, and width measure basically captured the structure of a graph using a single number. So in the terms of tree width, the number that we associated with the graph was the tree width of a graph, and it's just one number. Similarly, we could say the degree of a graph is also just one number. But soon we will not only associate a single number with the graph, but we will need like a sequence of numbers. And these sequences of numbers, they could be very long, they could even be infinite. And so a single number to capture the structure will no longer be enough. And that's why we will consider graph classes. Instead of a single graph, we will have to talk about classes of graphs. And at first, this will feel a bit strange, but over the course of the next lecture, I will hopefully convince you that this is actually necessary. And if we want to get the kind of results that we're interested in, this is the most natural way to talk about this. But let's see first what we can say about tree width using this notation about infinite graph classes. So we would say that a graph class C, usually we use this calligraphic C here. Some people also use calligraphic G for graph classes. We say that it has bounded tree width if there exists some constant C such that all graphs in the graph class have tree width at most C. So for every graph, the tree width should be bounded by some constant that depends only on the graph class. So the class of all graphs does not have bounded tree width because graphs of size n have tree width n, and n can grow very, very large. But some classes have bounded tree width. You could say, for example, the class of all graphs with tree width at most 7, they have obviously bounded tree width. And the confusing and important thing to note now is that we started talking about classes of graphs. So we no longer talk about single graphs, we always talk about infinite classes of graphs. It makes no sense to say this graph has bounded tree width, because this graph always has some constant number as their tree width, like 1 million. And I don't know, is 1 million bounded or not bounded? It's a number. So we can only say something about infinite sets, whether the threshold is always bounded. If you consider a class that is only finite, then naturally the tree width or any other width measure is bounded. So it only starts making sense if you start talking about infinite graph classes and no longer about single graphs. And generally, if we are not only interested in tree width, but it could be any other width parameter, we can say that a graph class has bounded x, where x could be bounded tree width, bounded degree, bounded click width, or whatever. If there exists a constant that bounds the width measure x for every graph in our class. So every graph in G should have x smaller than c. So this way you get bounded degree and all the other similar width measures. And using this new notation, I would like to rephrase what we have already, our Courcelle theorem. So now we have a graph class C that has bounded tree width. And if we want to run Courcelle theorem, then it would solve evaluate an MSO formula and some function of the phi, some function of the tree width times n. But now the tree width of every graph in C is bounded by some constant C. So our running time actually is some functions of phi and C times n. But C is a constant now. So we can put the C into the function and then interpret, say, f prime is a function f of phi and additionally C. So can interpret our running time now as a function that depends only on phi and no longer on the tree width of the graph. So this way, Courcelle's theorem reads as follows. We have graph class C with bounded tree width, and then there exists a function f. And now the important thing is this f depends on our class. So for every graph class, you would get a different function f, such that we can evaluate MSO sentences on a graph in some function that depends only on the length of the formula and no longer on the tree width. And if you want to strive for the ultimate shortest way to state Courcelle theorem, then we can next notice that if you want to express a problem in MSO, then the formula that expresses the problem has some constant length. So for 3 coloring, the formula has size O of 1. So in particular, f of phi would also have size O of 1 if you're considering a single fixed problem. And then you can phrase Courcelle theorem like this. If you have a class with bounded tree width, then you can decide an MSO expressible problem in linear time. Because both the length of the formula and the tree width, they're both bounded by some fixed constant, and then they fall into the O of the O notation. And the thing left with is only O of n. And this is a very nice way, I think, to write these kind of meta theorems. Of course, you need a bit of background to understand all this, and it's but it's very succinct, I think. Other questions about this so far? If not, then I would like to talk about inclusion diagrams and how to talk about these graph classes. So now we can talk about properties of graph classes. Graph class can have bounded tree width, or can be planar, or can have bounded degree. And we can draw these properties in boxes, and then we can draw arrows between those boxes. Can somebody tell me what these arrows could mean? Why is there an arrow from forests to bounded tree width?
Every graph that's in the box forests would also be contained in box bounded tree width in the class.
Almost. So you say every graph is in this box. If it's in that box, every graph class actually. So we have to, this is now a bit confusing. We have to talk about graph classes. So a graph class, if a graph class consists only of forests, then the graph class has in particular bounded tree width. And now let's say we define a new notion. Let's say call it blub width. And the blub width of a graph is simply twice the tree width. Then the width measure, tree width, and blub width are a little bit different. But if a class has bounded tree width, and the tree width is bounded by constant c, and in particular the blub width will be bounded by 2c. So we could draw an arrow like this. Bounded tree width implies unbounded blub width, and the other way around as well. So this way, by considering this infinite graph classes, you can talk about the equivalence between width measures. So they no longer need to be absolutely equivalent, but you need the property, like if one thing is bounded, then the other thing is bounded, and the other way around. So this simplifies it sometimes. For example, you don't need to distinguish between click width and rank width because one is bounded if and only if the other thing is bounded. Okay, so these 4 classes, they should be quite familiar to you guys. And now we could wonder, like, what do these classes all have in common? So, and it seems like graphs with bounded tree width, they only have a linear number of edges. So if the tree width is W, then the number of edges, you can show that it's at most W times N. Similarly, planar graphs, you can show that they only have 3 times n edges. And of course, if your graph has constant degree, then also you only have a linear number of edges. So it seems like all these classes so far, they have in common that they're sparse. But like, what does it really mean to be sparse for a graph? The intuitive idea would be that a graph is sparse if it only has a few edges, but there will be some very important differences that we're going to see soon. So if we would say that every graph is sparse if it has few edges, then basically there's a very cheap way to make every graph sparse. So let's start with this graph. It is now an arbitrary graph, maybe a dense one. But if we subdivide the edges like this, then it becomes sparse, because for every vertex here, you have 2 edges that are adjacent to it, or other way around. For every 2 edges, you have 1 vertex. So in this graph, the number of edges is bounded by twice the number of vertices. So the average degree is 2, and so it's a rather sparse graph. But I would argue that this graph still contains essentially the same information. It's still the same graph, just subdivided. And you will have to decide whether you would consider this sparse or not. So if you say this would be a sparse graph, yes, then we will end up with the notion of degeneracy, which we will introduce formally in the next lectures. But this notion of degeneracy is not very satisfying because it's not as algorithmically tractable as different notions of sparsity. Because like first order logic, for example, it can recover the original graph. It can say 2 vertices are adjacent if they have distance 2, kind of. So this way you can evaluate the formulas on the original graph, even if you only have access to the subdivided graph. So if you want to have like a bit more robustness in your definitions, you will end up considering this a not sparse graph. So we will forbid this kind of cheating by subdivisions, and this will lead to the notion of bounded expansion and lower dense graph classes that we will introduce soon. So you notice these are now measures for graph classes. So you cannot say a graph has bounded expansion. You can only say a graph class has bounded expansion. This is why we did this whole business with the graph classes. And yeah, in the next lectures, we will consider this different notion of sparsity, where subdivisions are not considered sparse. And this will lead to some graph classes like this. So we will introduce lower dense graph classes, which will be at the very, very top of the hierarchy. And below, you would have like bounded expansion and locally bounded tree width that generalize all the graph classes that we've seen so far. And they're on the second level, they're incomparable. So you cannot compare locally bounded tree width, bounded expansion, and the other way around. And but actually, if you want to draw a complete picture of all the sparse graph classes, you can think of like there's this very nice picture by Felix, where at the bottom of the hierarchy, you have something like very simple, like star forests or just paths. And then as you go up in complexity, you end up in the end here with lower dense graph classes. And there's a lot of stuff in between. You have the planar graphs in between, you have tree width in between. And we're not going to talk about everything in this picture, but hopefully the most important bits of this picture. But the important thing is, like once you are above this bounded tree width case, maybe still here. Once you're above this line, you cannot do MSO model checking anymore. And so MSO1 will be too powerful for the sparse graphs that we're interested in. Because, for example, independent set, coloring dominated sets, they're all NP complete on planar graphs or bounded degree graphs. However, we will consider first order logic, and we will notice that first order logic will be just the right logic for these sparse graph classes. And the main result that we're going to prove in the second half of the lecture, very roughly stated, will be that if you have a sparse graph class C, then you can evaluate an FO formula, so a first order logic formula on graphs from this graph class in time some function of the formula length times n. So this is a simplified statement. It's not quite the whole truth because, for example, I didn't specify like what is a sparse graph, and we will dig into this a bit more in detail in the next lectures. But before we talk about the sparse graph classes further, I would like to talk about this aspect of the statement about the first order logic, what you can do with it, what you cannot do with it, and why it's an interesting logic to consider. Or are there, up until now, any questions about sparsity or anything? If not, then let's consider first order logic. So the difference between first order logic and second order logic is that you're no longer allowed to quantify over sets of vertices or sets of edges as well not. So you can only quantify over single vertices. So we have this vertex variables, usually denoted by lowercase letters, and you can have these relations and you can quantify existentially and universally over the vertices. And usually, again, we are only allowed the relations adjacency and colors. And if we fix these signature tau, then we call the logic FO. And this is the logic that we're going to work with. And can again talk about how expressive this logic is. So clearly it will be less expressive than MSO logic because we don't have the set quantifiers anymore. But can we, for example, express that the graph has an independent set of size k?
For a fixed k, it's not a problem because we can just take k variables and check for each pair that they are not adjacent.
Exactly. We can do it like this. We can write there exists x1 to xk, and they should not be adjacent, and they should not be equal. And yeah, you mentioned correctly that the length of the formula depends now on k. So if k gets larger, the formula gets larger. But so the length of the formula and the running time will depend on k. But this is something that we already accepted, that if you want to find an independent set of size k, then like on planar graphs, you already have to do something like 6 to the k times n. So the running time will depend on k. And so in this case, it is okay that the length of the formula grows with k. Next, this is similar. You could ask, is there a dominating set of size k? Can this be expressed using FO? Yeah, you can do it like this. You can say there exist vertices x1 to xk, such that all other vertices should be dominated or equal to the k previously chosen ones. So all vertices y should either be adjacent or equal to one of the xi. So this formula is not true if and only if the graph has a dominating set of size k. So far, so good. So you can express some nice properties with it. How about you checking whether the number of vertices is even or not? So in the exercise, we already discovered that you cannot even do this in MSO logic. So particularly you can do it with FO logic, but except this time we will be able to prove that you cannot do it. Or another statement, you could wonder whether a graph is connected. In MSO, we could do this by saying for every partition, there should be an edge between the two partitions. For first order logic, it will turn out that you cannot even express connectivity. So in the sense, first order logic can only make very local statements about small regions of the graph, but on the connectivity can be a very global property. The paths that connect to vertices could be very, very long. So yeah, there's for some bits, first order logic is very nice, but there's these trivial properties like connectivity or evenness that it's having trouble with. But there's another very nice connection for first order logic, and you can kind of motivate it using databases. So database languages such as SQL, they build upon first order logic, or like they build upon like relational calculus, I think it's called. Relational calculus builds upon first order logic. So you can have these nice analogies between evaluating logical formulas and database queries. So in a database query, you may be interested in enumerating all answers to a query. Like, give me everybody that is below the age of 30 and lives in that region or whatever. And similarly, you could have like a first order logic formula with 3 variables, and then you could enumerate all tuples that satisfy the formula. So this kind of corresponds to enumeration of queries. Or if you simply have a Boolean query, then this is the same as evaluating a sentence on a graph or in a structure. And like, but SQL and these logics, they usually have much richer toolkit. For example, you have like a count operator, which states, which checks whether a certain number of elements with some properties has a certain size. Like, is the number of blog posts from last year larger than 100? But there also exists extensions of first order logic, which have extra separators that can also count. And so this now motivates like some variants of the model checking problem. For example, the basic version is also phrased the query evaluation problem. Here you have a graph and a sentence, and you want to decide whether the formula is true on the graph or not. So this is just an evaluation of the formula. Query enumeration would be the following. You have a formula with 3 variables, and then you want to find all tuples that evaluate to yes if you plug the tuples into the formula. So if your formula is k vertices from an independent set, then the query enumeration would enumerate all independent sets of size k. And another variant would be query counting. Here, instead of enumerating all the satisfying assignments, you simply want to count them. So this way, if I again states that x1 to xk from an independent set, the answer you would get would be the number of independent sets of size k. And we have the same problem as with the model checking problems one, as in that the model checking, even for first order logic, is p-space complete. So before we noticed that MSO model checking is p-space complete, but even for the simple first order logic, it is p-space complete. And this is, of course, because the formulas can be very long. So even on planar graphs, it is NP complete. So if you reduce from independent set, then you can write down this formula that expresses the graph as an independent set of size k. And if you could evaluate it in polynomial time independent of k, then of course you would solve independent set on planar graphs. So we can't really hope to evaluate very long formulas. But usually if you have like a database system, your database can be huge and very, very big, but the queries that you're writing, they tend to be small. So most database queries, they have very, very small size compared to the size of the huge database. So it would be fine for us to parameterize by a formula. So again, we would like to have a function of the length of the formula times some polynomial in the graph. So this is something we would be fine with. But so far we don't have that yet. So we can get a simpler, a different statement that is a bit weaker. So on every graph, you can evaluate an MSO formula in time size of the graph raised to the length of the formula. So for every fixed formula, you get a polynomial time running evaluation algorithm, but the degree of the polynomial equals to the length of the formula. So here's a very quick proof on how you could evaluate some formula phi in G to the length of phi. First thing you would do is maybe convert the formula to pre-next normal form. Pre-next normal form means that in the beginning, there's all the quantifiers, and afterwards, there's a single formula phi that contains no quantifiers anymore. So we've kind of pushed all the quantifiers to the beginning of the formula. And let's say we want to evaluate this formula here, exists x, such as for all y, exists z, phi is satisfied. Then we could branch over all the possible values that x could have. X could be v1, could be v2, v3, up to vn. So we get n different branches for the value of x. And for each branch, we plug the value that we choose, we plug it in for x. So here we chose x equal to v3, so phi is now evaluated on x3 instead of v3 instead of x. Next, we have to branch over the y. So here again, we have n different choices for y, and we plug the value into the formula as we chose it. And at the bottom, we have for the existential quantifier again, n different values. And now our formula, it contains no variables anymore. So for every free variable in phi, we've chosen an assignment. So it's a quantifier-free formula. Every variable is assigned. We can simply evaluate it in constant time by checking whether all the edges that should be there are there, and all the right vertices are equal or adjacent and whatever. So this formula can be evaluated in constant time. And next we can propagate the truth values here. So for the leaves, we can write down maybe this one evaluates to true, this one evaluates to false, for true, this one evaluates to false. Next here, we want to decide in the next level whether they evaluate to true or not. But here we can see there, we only need to find some z that satisfies the formula. So we can say that this node evaluates to true if and only if at least one child evaluates to true. So in this case, the v3 child, for example, evaluates to true, so this node also is true. Differently here with the universal quantifier, so this thing needs to be satisfied for all assignments. So if here everything is yes, then also this is yes. So this way we walk all the way up to the root, and then we see whether the formula sits, the root formula, which is our original formula, is satisfied or not. And this tree, of course, now has a size at most n to the phi, because like with every quantifier we branch n times, and the number of quantifiers is bound by the length of the formula. So we get the runtime that I promised, because once you have built the tree, you can evaluate it very quickly. So the main runtime depends only on the size of this evaluation tree. And next you could wonder, like, can you do better than this? And here I have a negative answer. So it's not quite an absolute answer, like we don't have absolute answers in computer science, at least on the negative side. It's again based on a hypothesis, this time of the strong exponential time hypothesis, which everybody believes to be true. So based on this hypothesis that you can show that you cannot evaluate formula phi on the graph G in the running time that is faster than G to the, and now you have quantifier, number of quantifiers minus 1 minus epsilon. So what you can get is something like G to the Q minus 1. This is possible, but as soon as you want to get a little epsilon better than that, it's not possible anymore. So in a sense, this branching algorithm that we talked about on the last slide is basically the best possible thing that is known. So this is a bit disappointing. The very trivial algorithm is the best algorithm that is known. Any questions about this so far? Okay. So, but I promised you that on certain graph classes we could do better than this trivial algorithm. We can get a real FPT algorithm parameterized by the formula. And so we have like a couple more minutes. So for a bit now, and for the next lecture in the beginning, I want to talk about like what can be expressed in first order logic. So here was an overview, like independent set, dominating set can be expressed, parity or connectivity cannot be expressed. And how could we prove this? Like in the exercise last time, we said we don't know how to prove this yet, but now we can actually prove that certain set properties cannot be expressed in FO. So a proof that something can be expressed is easy. You write down the formula. Proof that something cannot be expressed is something we will talk about now. And for this, we again need the quantifier rank, something we talked about already, the maximum number of nesting of quantifiers. And now we will need some new notation. So we say that the graph G and the graph H is Q equivalent. So with equivalent say symbol with the Q in the subscript, if for all first order sentences phi of quantifier rank that was Q holds, that phi is satisfied in the first graph if and only it is satisfied in the other graph. So they're Q equivalent if and only if they satisfy exactly the same formulas of quantifier depth, the quantifier rank and loss Q. So first order logic cannot distinguish between those two graphs using only Q quantifiers. So you notice they're Q equivalent if and only if they have the same Q type. And let's say we want to prove that first order logic cannot distinguish between connected and disconnected graphs. Then the way we can show this is we show that for every Q, there exists a connected graph GQ, and there exists a disconnected graph HQ, such that first order logic with Q quantifiers cannot distinguish GQ from HQ. And how does this lead to our proof? So let's assume now that we had a formula that could distinguish between connected and disconnected graphs. So the formula evaluates to yes, if and only if the graph is connected, for example. Then this formula, it would have a fixed quantifier rank. It would have a quantifier rank, let's say Q, for example. Okay, so we have this quantifier rank Q now of our formula that can distinguish connectivity. But now the graphs GQ that we constructed earlier, the graph GQ and HQ, they are Q equivalent. So they have to evaluate to the same first order logic formulas. So in particular, the formula we just assumed that existed, it is either true or either both false on both of those graphs. But this is a contradiction because we assumed that the formula is true on one graph and false on the other graph. So now we have a contradiction, and we know that first order logic cannot express connectivity. And what we did here, the magical part, is this step, where we assumed that we can have these Q equivalent graphs. And this is something that I wanted to talk to you about next. How can we express that certain graphs are Q equivalent? And this is something that we will do using so-called Ehrenfeucht-Frézé games. It's a game played between two players, a duplicator and a spoiler. And it's played on two graphs, G and H. And the game will be phrased in such a way that the duplicator wins the game on these two structures if and only if G and H will be Q equivalent. And Q is here the number of rounds of our Ehrenfeucht-Frézé game. And let's see how the game proceeds. The first thing is the duplicator picks a vertex. So it picks a vertex either in G or in H. And if it picks a vertex in G, we call it GI. And if it picks a vertex in H, we call it HI, where I is the index of the move we're in. So in the first move, we pick, for example, G1 and G. And now the spoiler has to pick an accompanying vertex. So if G1 was picked, then the spoiler has to pick H1 and the other way around. So let's say now the spoiler picked the vertex H1 and H. And we repeat this now a couple of times. So first, the duplicator picks a vertex. Maybe I'm confused. I have written it down differently. Maybe the spoiler is picking the vertex first and the duplicator has to copy the moves. I think I've written the wrong way around on the slides. So anyway, one player picks a vertex and the other player has to like mimic this move. So if H1 was not picked, then the other player has to correspond with G1, and if H2 has been picked, it corresponds with G2. And the duplicator wins if both graphs are equivalent. So the duplicator wants to make sure that Gi and Gj are adjacent in G, if and only if Hi and Hj are adjacent in H. So next thing, one player would have to choose an H3. H3 would need to be chosen now. And I would say this is now impossible because G3, in this picture here above, G3 is adjacent to G2. So the other player would have to pick H3 adjacent to H2. And this is now no longer possible because no matter where he puts it, the only vertex that's adjacent to H2 is H1. So clearly the player made a bad move here. So this should be a spoiler, I think. This should be a duplicator. So the duplicator made a bad choice here in picking the vertices like this. So maybe a smarter way to play would be to mimic the behavior better. So if the spoiler picks G1, then maybe the duplicator corresponds with H1 there. Like the vertex is very similar. It picks G2 there, then the spoiler and the duplicator corresponds there. So far, everything is isomorphic, right? G1 and G2 are not adjacent, and H1 and H2 are also not adjacent. And next, maybe with H3 here, duplicator corresponds with G3 there. So far, everything good. H4 here, G4 here, everything good. But now, if H5 is chosen here, then the duplicator cannot find a matching vertex anymore. No matter where he picks, that puts G5, it will always be adjacent to some vertex, while here below it is required that H5 is not adjacent to any of the vertices that have been chosen already. So in this game, the spoiler would win at some point. And generally, you can show that two structures are Q equivalent if and only if the duplicator has a strategy to win the Q round Ehrenfeucht-Frise game. And in the next lectures, we will use this to show, for example, that first order logic cannot express connectivity, cannot express parity. We will even use this theorem to prove a variant of the Pfefferman-Watt theorem for first order logic. But I think for today, we're kind of through with our time. Are there any questions up until now? Any questions in the chat? I guess not. If not, then thanks everyone, and we'll see each other next week.